We started the basic knowledge of sinusoidal alternating current earlier. Next, we will study the characteristics and functions of components in sinusoidal alternating current. In a sinusoidal alternating current circuit, except for an AC voltage source and an AC current source in the circuit, it also includes resistance, capacitance, and inductance. These are all components, basic elements of a circuit. In this lesson, we will study pure resistance element and study the characteristics and functions of sinusoidal alternating current. With a single parameter, the circuitry of pure resistance is the simplest AC circuit. Which electrical appliances are pure resistance elements? In our daily life and work, the equipment and components we come into contact with include incandescent lamps, soldering irons, electric furnace, etc. They are all resistive loads. The product outline diagram is shown below. It is connected with an alternating current power supply, forming a pure resistive circuit. Let's analyze it. We will analyze the pure resistance element with a single parameter and its relationship with voltage of sinusoidal alternating current and current. Figure 3.3.1 contains 4 subgraphs. Figure A is a pure resistance circuit with a single parameter alternating current. Figure B represents the voltage across the pure resistance, with the waveform diagram showing the relationship with current. Figure C is a pure resistance element, with the phasor diagram representing the voltage at both ends and the current flowing through it. Figure D illustrates the instantaneous power waveform diagram on the pure resistance. In the resistance circuit shown in the above figure A, if the sinusoidal voltage is applied across the resistor R, U equals UM sine omega t equals root 2 times U sine ohm t. According to the expression, the initial phase of the sinusoidal voltage across the resistor is 0. According to Ohm's law, the current flowing through the resistor R, I equals U over R equals UM sine ohm t over R equals IM sine ohm t equals root 2 times I sine ohm t. As can be seen from the above expression, IM equals UM over R or I equals U over R. By calculation on a pure resistance element, the voltage and current waveforms are as shown in figure B. From the chart, it can be seen that the voltage and current waveforms change at the same speed and reach the maximum at the same time. Simultaneously reach the minima, that is, in the same step, but different in magnitude. Thus, it can be concluded that the relationship between voltage and current magnitude and the relationship with phase is as follows. The frequency of voltage and current is equal. Voltage and current are in phase. That is, phi ui equals phi u minus phi I equals 0. The maximum of voltage and current, effective value and phasor are all in line with the Ohm's law. That is, the maximum voltage phasor is equal to the magnitude of resistance multiplied by the maximum current phasor, or voltage Rm's phasor, is equal to the magnitude of resistance multiplied by the phasor of current effective value. Moreover, voltage effective value of current and resistance R are all observe the Ohm's law, namely U equals Ri phasor of voltage and current, as shown in figure C above. Voltage across resistor R in phase with the current flowing through R, and its instantaneous value, amplitude, and effective value are all conforming to the Ohm's law. Next, let's learn the instantaneous power of the resistance element R is the instantaneous power of the lowercase letter p. P equals Ui equals Im sine omega t times sine omega t equals Ui 1 minus cosine 2 omega t. The resistance power waveform is as shown in figure D above. At any moment P greater than or equal to 0 indicates that the resistors are consuming electric energy. Resistance is an energy-consuming element. The electric energy obtained from the power supply will be converted into heat energy. What is usually called power in a circuit refers to in a period. The average value of instantaneous power is called average power, also known as active power, represented by the capital letter P. The unit is watt, abbreviated as W, represented by the letter W. Average power on resistance equals within one single period, integral of instantaneous power with the time, and then divided by the period size is the average power calculated by formula. Finally, the resistance is obtained. The average power P is equal to effective value of voltage across resistor. Multiply the effective value of the current flowing through the resistor. It is also equal to the square of the effective current multiplied by the resistance R, or equal to the square of the effective voltage divided by the resistance R. Above, we learned about pure resistance elements. With a single parameter, knowledge of sinusoidal alternating current, to test the learning effect, let's look at a question. Example. There is an electric light. The voltage applied to it is U equals 311 sine 314 T volt. The lamp resistance is R equals 100 ohm. We need to get the current I, effective current value I, and power P. If the voltage angular frequency changes from 314 rays per second to 3,140 rays per second, we need to determine the effect of this change on the effective current value and power. Let's see how to solve this problem. According to the meaning of the question, we can know from the Ohm's law that the instantaneous value I of current is equal to the instantaneous voltage U divided by the resistance value. That is, I equals U over R equals 311 sine 314 t over 100 equals 3.11 sine 314 t ampere. From the expression of the instantaneous value of current, we can find that the effective value I of current is equal to the maximum value In divided by the square root of 2. That is, 3.11 divided by the square root of 2 equals 2.2 amps. The magnitude of power is equal to the square of the effective value of current multiplied by the resistance. That is, P equals 2.2 times 2.2 times 100 equals 484 watts. Because the resistance value of resistance and the magnitude of current are both independent of frequency, the effective value of current and power remain unchanged when the frequency changes. In this lesson, we learned about the resistance element passes through a single parameter. Characteristics and functions of alternating current from the magnitude of voltage and current. Phase relationship expansion learning. Finally, in order to deepen your understanding and comprehension of this lesson, I've provided 2 questions for you to discuss after class. This concludes our lesson for today. See you next time, students.